Hello. In the last video, we discussed about the flow and terminology associated with genetic algorithm. And towards the end of that video, we're looking at a sample problem, uh, a Gaussian curve with a little bit of noise added to it. It was just a function of x, and we wanted to maximize it in the range 0 to about 128, and we wanted 4 decimal place precision. Discussed about binary encoding and concluded that each candidate solution will have 21 bits, reserving 7 for integer value and the remaining 14 for the fractional ones. Now let's look at a quick iteration of the problem. Just a quick reminder again, uh, the range that we'll be optimizing the problem in is 0 to 128. That is just being imposed by the fact that the length of a candidate solution is 21 bits. That is, uh, it can cover from minimum 0 to maximum about 128. We're not adding in any additional constraints like just keeping our value uh, till 100 or something like that. We'll be discussing constraints in the next video when we try to solve the 0 1 knapsack problem with genetic algorithm. Yeah, let's look at a quick iteration now. So here you can look at examples of what candidate solutions look like. So this is the encoded part. You're able to see that they have 21 bits, 1 and 0. And on the right hand side you see in red the corresponding floating point value with 4 decimal places. The next step would be for us to calculate the fitness of each individual in the generation, and we decided that the fitness function would just be the value of x, since we're trying to maximize this function. And in red you can see the corresponding fitness of each of the 10 solutions that we're starting with. Next we sort the population in descending order of fitness, so the best solutions are at the top. Uh, for this problem, we'll be using elitism. We'll be keeping the value at 2. So two of the best solutions, say x1 and x2, they'll be directly passed on to the next generation without any changes. That means a new generation already has two individuals, and since we are keeping the size of the generations constant at 10, so we still need 8 more to make the population size 10 again. Some variants of genetic algorithm, as I said, change the sizes dynamically, but we're keeping it static. Our goal now is to create those 8 new candidates through crossover and mutate them. For this problem, we'll just be using a single point crossover, but you may choose to use a double point one or both of them. So it's really up to your discretion. We'll just be using a single point one, and as we know, a single point crossover produces 2 children at a time. So in order to get to 8 children, which is what we need to complete a population for the next generation, we'll need to perform 4 crossover operations. Now before selecting the parents for crossover, we need to normalize the fitness values, but because of fitness function might produce negative numbers, we need to first share the entire fitness vector by just subtracting the minimum value only if it's less than 0. If they're above 0, we don't need to perform this operation. After we've shared them and every value is non-negative, then we normalize by dividing each fitness by the total sum of fitness for that generation, so that all of these add up to 1. We'll be using this as the selection probabilities, this normalized vector. And now we just repeatedly select two parents, form crossover, the crossover results into offsprings. We apply the mutation operator to these offsprings and add the resulting children to the next generation, and we'll do this 4 times. So now by the end, our second generation has 10 individuals again, 2 carried over from elitism and 8 newly created through crossover. Alright, let us now move on to the Python implementation of genetic algorithm for our sample problem. Let us start by importing in relevant libraries and setting the numpy seed for reproducible results. Alright, let's now define a few constants, starting with target length as 21. This is just the length of the candidate solution, or the number of bits, the binary bits in our candidate solution, which are 21, 7 for integer, 14 for the fractional part. Then we have n equals 10. This is just the size of our population. Then we have n iterations as 500. This is the number of generations that will be evolving through. And setting the elitism constant to 2. This just means that we'll be passing on the top 2 solutions from each generation to the next generation without making any changes. And then we have the create population function, which takes in population size and target length as its parameters. This function just simply creates an initial population of population size, and the length of each candidate solution will equal the parameter target length. Let's quickly run it for 10 and 21 and persist the results in a temporary population variable. Population size equals n and target length equals target length. Let's see what this variable stores. Right, so this is our initial population. You can see we have 10 candidate solutions, each having 21 binary bits. Moving to the second function, which is binary to decimal. This function simply just takes in the population as a parameter and returns to us the corresponding numeric value of the binary encoded solutions. It also takes in the number of integer bits and the number of fractional bits as a parameter. We're defaulting it to 7 and 14. Now this function simply works by separating out the integer and fractional bits and creating powers of 2, raising the binary bits to the corresponding powers of 2 and summing up the result. And it just returns the numeric value rounded to 4 decimal places. Let's pass our temporary population to this function. And let us persist the results. Alright, so these are the corresponding numeric values for this particular population. Moving on to the next function, which is fx. This is just the objective function. For every value x passed here, we get the corresponding value of fx, and we've chosen this as our fitness function as well. Let's run this on, and the important thing to note is that this works on numeric values and not on the encoded population values. So we'll be passing in this variable to fx, and let's assign this to temp fitness. So these are the values of fx for these values of x, and here you can see that we can get negative values as well. We'll be factoring this part in when we do the selection of crossover candidates, which brings us to the next function, which is select crossover candidates. It just takes in the population as a parameter and its corresponding fitness, and it just provides us 2 candidates that have been selected for crossover using the roulette wheel selection method that we discussed in the last video. It just starts by calculating the minimum fitness for the particular generation. If it happens to be a negative value, we'll be sharing the whole fitness vector of that generation by that value, so that we have all values as non-negative. Then we create then we just normalize this fitness vector such that all the values now add up to 1, and we'll be interpreting this newly created vector as the selection probability of the of the parameters, sorry, of the population that has been passed. And finally, once you've selected two candidates, we'll just provide those candidates out of the population of the current generation. Let's see how this works by passing in the temporary population and its corresponding fitness. Let's just name this as parents. Okay, not fitness, temp fitness. Right, so we have the two selected candidates. So these candidates have been selected for crossover. Let's go to the crossover function now. This candidate just takes parents as a parameter, and the parameter parents will be looking just like this. So two candidate solutions, and this function implements the single point crossover. It just simply starts by picking randomly a breakpoint, then create the children array, which looks just like the parents array, because again two parents give out two offsprings, and then we just swap the genes of parent 1 and parent 2 at the breakpoint, as we discussed while we were discussing in detail about the single point crossover, and then it just returns the children array. Let's run this on the parents that we've selected. Actually, let's also print the breakpoint. And printing out the offsprings. Right, so this printed value is the breakpoint, and just by looking at this array, the offsprings array, and this one, the parents array, we'll be able to see that the binary bits have been swapped after the 8th bit, which is what this breakpoint signifies. Then we have the mutate function, which takes in prospects array as its input. The prospects array will look like this because we'll be mutating the offsprings. This function just simply defines the flip probability as 1 divided by the target length, and then creates a mask picking values from 0 to 1 for of the length 21 and checking them against the threshold. If the threshold conditions are met, we flip that bit. Then we have the display and calculate fitness function. These are just helpers. Moving on to the main genetic algorithm loop. So this starts by first of all creating an initial population using the create population function. We'll be persisting the top n candidates for each generation to look at them later on once the whole loop has ran. And this top n will also be a parameter for this the main loop of genetic algorithm. Then we have the loop from 1 to the total number of iterations that we want to do, 500 in our case. And for each generation, we'll start by calculating the fitness for the population. For the first one, it'll be the initial population. Then just sorting our candidate solutions and fitness in descending order so that the most fit solutions are on top. And yeah, as I said, we'll be persisting the top n records. This just does that. And Then we create the next generation. The next generation will have the same number of candidate solutions, that is 10. First, we fill the first two solutions from the current population. So the current population top two solutions will become the first two solutions in the next generation as it is. Now that we have filled in two places, we need to fill in the remaining 8 places. So we'll be running a loop for that. That will do crossover 4 times. So first of all, we'll select parents from the current population and corresponding fitness, and we do crossover, mutate, and add in the children to the next generation. Yeah, and once we have done crossover sufficient number of times such that we have the complete next generation ready, we just assign the next generation array as the population array and continue this whole loop again until we've completed the required number of iterations. Let us now remove the unnecessary things from the notebook and run it from the beginning. Right, so running the whole notebook now. Let's look at the results now. We persisted the top 3 candidates for each generation. Let's display them in a way that we can see the first generation, then the 10th and 20th, and going all the way to the last generation, 500. In this manner, the best solution to our problem was 64.4469. Let's see, when did we actually reach to this solution. Starting with the very first generation, the top solution here was 67.7245, attaining a fitness of 1.872148. You can see that this is the encoded solution. Moving to further generations, you can see in somewhere between the 50th and 60th generation, we've reached very close to our actual solution, rounded to 4 decimal places. We've reached 64.4468. We can see that in the 60th generation, this is the top solution. And to actually just reach the best solution to our problem, we reached it somewhere between the 270th and 280th generation, because we can see in the 280th generation that the best solution is 64.4469, and yeah, this is the encoded value for that solution. Let us now look at a quick animation just to see how our solutions evolved and what was the top solution for each generation. So that's about it for this video. See you in the next one, where we'll try to solve the 0-1 knapsack problem using genetic algorithm and discuss how to implement constraints inside algorithm. Thank you.